Okay, good. So I want to keep going with rewriting the second term. Okay, so let's just isolate off the second term. This is what I want. Let's duplicate it. Good. And let's maybe leave a little bit of space and we'll work down the bottom here. Good. Okay. And let's work in blue. Good. Okay, so what I want to do with this term, I want to rewrite it a little bit. And the manipulations that I'm doing now might not look intuitive to you at all. And well, people had to play with these expressions and find out what were useful ways of manipulating them. So this is being written down with a lot of hindsight. So what I'm going to do is I'm going to introduce a delta function. So we'll have an integral d4p over 2 pi cubed. We'll have a z, theta of p naught, e to the minus I p dot x minus y, and then we'll have an integral dA squared delta of p squared minus a squared sigma of a squared. And what you can see is I haven't changed anything, because if I do the integral over a squared, sigma of a squared is just going to become sigma of p squared, and then the first line and the second line are obviously equal. Good. But what I'm going to do now is I am going to integrate over that delta function, but not with a squared. I'm going to integrate over the delta function using p naught. So we'll have an integral d3p, so let's keep the d3p here, over 2 pi cubed. We will have a z, an integral dA squared. Let's put the sigma of a squared there. Then we will have an integral dp naught. We will have a delta of p squared minus a squared. We will have a theta of p naught, and we will have an e to the minus I p dot x minus y. So take a look. I think that we've captured all of the terms. Good. So to do the integral over p naught, the first thing that we need to know is where is the delta function satisfied. So writing out what is p squared minus a squared, well, this is going to be p naught squared minus p dot p minus a squared. And remember that this is equal to naught. That's where the delta function gets a contribution. So if we solve for p naught, we find that p naught is equal to the square root of p dot p plus a squared. And usually it should be plus or minus, but theta of p naught implies that we should choose the plus sign of the square root, because theta of p naught means that we only pick up the positive root, the root of p naught being positive. So that's the root that we're going to pick up. A few things that we should also bear in mind. Remember your rules for integrating over the delta. What sits inside the delta is p naught squared, but our integration variable is p naught. So the simplest way to deal with that is to replace dp naught by dp naught squared over 2p naught. And I think that you can see that those two are equal. And when we now do the integral over p naught squared, it's absolutely fine to just replace p naught by the square root of p dot p plus a squared everywhere, as long as we also keep the 1 over 2 p naught hanging around. Good. So let's see, what do we actually get? Well, we've got an integral d3p over 2 pi cubed. Good. We'll have z integral dA squared sigma of a squared. Then from the integral over p naught, we've got 1 over 2 times the square root of p dot p plus a squared. So that's coming from the measure. That's this contribution that I just outlined in the box. Then the theta of p naught is gone, and we've got the exponential. So what's the exponential? Let's just write it out in detail. It'll be e to the minus I we no longer have P naught. We'll have P dot P plus A squared times by Tx minus Ty, and then we'll have plus I P dot into X minus Y. And I just want to rewrite this in a slightly different way as follows. I can write this as Z, that's just a constant. I can have an integral dA squared, sigma of A squared. Then I will put integral d3p over 2 pi cubed to square root of P dot P plus A squared. And then what's the exponential at the top? Well, it's exactly what we had before. E to the minus I square root of P dot P plus A squared into Tx minus Ty plus I P dot X minus Y. So we didn't do very much in this step. We just pulled the Z and the integral, the A squared sigma of A squared out, and we wrote everything else that we have left. But what is interesting about this, now I want to remind you of the function that we defined, delta plus. So delta plus of x minus y, comma mp squared was an integral d3p over 2 pi cubed 2 omega p, and then that exponential e to the minus I p dot x minus y, and inside here, the p naught was omega p. So if we look at this expression over here, what is this? Well, this is z integral dA squared sigma of A squared, and then we've got delta plus of x minus y comma A squared. So that's the form that I wanted it in. So let's add it in over here. Okay, so the second term, that's what we've been manipulating. We've now got a different form for it. So this correlator is z times delta plus x minus y comma mp squared plus, then we've again got a z, we've got an integral dA squared, we've got sigma of A squared, and then we've got delta plus of x minus y comma A squared. Let's just make sure that we didn't mess anything up. No, I think that I got it right. Okay. So this is what we've got for this correlator so far. Now, that's the Wightman correlator, and that's the form that I wanted for the Wightman correlator. Now, I want to use this to write down what is the time-ordered two-point correlation function. And remember what that looks like, okay? We have got a theta function of Tx minus Ty multiplied by the vacuum expectation value of one ordering of the fields, plus the other theta function, Ty minus Tx, and the other ordering of the fields inside the Wightman function. Oh, too many y's here. Good. X's, not enough y's. There we go. So that's what we've got. Good. So we know what the Wightman function is. So now we can write down this time-ordered correlator. So let's do that next. Good, that's enough space. So this will be equal to theta of Tx minus Ty. Then we've got Z sitting here. Delta plus x minus y, comma, mp squared, plus z, an integral, the a squared, sigma of a squared, and then again delta plus x minus y, comma, a squared. And then we need to write down the second theta function, the ty minus tx. And what multiplies this? Well, we have to swap x and y because we've swapped the positions of the two fields inside the Wightman function. So there's the first term, plus z integral the a squared sigma of a squared delta plus. Now this is y minus x comma a squared. Good. Okay. Now, there's one more identity that I want to remind you of so that we can do our last rewriting of this answer. So, sorry, let me just get rid of this. Now, this has been used. We don't need it anymore. So let's remove it. Good. Okay. So the identity that I want now, I just want to remind you of something, jog your memories. This is something that we derived. If you don't remember it, you should go back and look at it. We studied the integral d4p over 2 pi to the 4, and then we had I over p squared minus m squared, and then there was Feynman's I epsilon prescription. We had an e to the minus I p dot x minus y. And we studied this in a lot of detail. What we did the integral over p naught. And to do that integral over p naught, we used the residue theorem. Okay, so that's what I'm referring to. We got that result. And now I'm just going to tell you what the result was. So remember, depending on whether tx minus ty was positive or negative, we had to pick up different poles, and we landed up closing the contour either in the upper half plane or lower half plane. But what the answer looked like, we had a theta of tx minus ty, and then we had an integral d3p over 2 pi cubed to omega p e to the minus I p dot x minus y, and we had an integral, a theta function of ty minus tx, an integral d3p over 2 pi cubed to omega p, and then we had an e to the minus I p dot y minus x. And remember, in both of these exponentials, p naught has been set to omega p. So that was the result that we obtained. Well, in the language that we have been using, what are these functions multiplying the theta functions? Well, if you look back, this is again nothing but delta plus integral d3p over 2 pi cubed to omega p e to the minus I p dot x minus y. So in fact, this is nothing but theta of tx minus ty delta plus of x minus y comma m squared plus, and there was a theta of ty minus tx delta plus y minus x comma m squared. So, when you see this particular form that's appearing, okay, so let's maybe put a red box around this. When you see this particular form appearing, a theta with a delta plus and a theta with a delta plus, well, you know that this thing actually can be written as an integral d4p over 2 pi to the 4 and I over p squared minus m squared plus I epsilon. But look at the answer that we're getting for our time-ordered correlation function here. We've got a theta function, and we've got these delta pluses sitting there. And over here, we've got a theta function and these delta pluses sitting there. So using this red box, I don't need to write a theta with a delta plus a theta with a delta plus. I can just write an integral d4p over 2 pi to the 4, I over p squared minus m squared plus I epsilon, and the exponential. So now using this formula, what do we get for our time-ordered correlator? Well, this is the formula that we get. Phi of x, phi of y, naught. So this is the time-ordered correlation function. There are two terms. The first term is an integral d4p over 2 pi to the 4. We've got an I times by z over p squared minus mp squared plus I epsilon. And this mp squared really is the physical mass squared of our particle. It's what experimentalists would measure. And we've got e to the minus ip dot x minus y. And then in the second term, we've got plus an integral dA squared. We have got an integral d4p over 2 pi to the 4. And we've got an I z sigma of a squared over p squared minus a squared plus I epsilon. And then we have an e to the minus ip dot x minus y. And this is the final formula that I wanted to get for our time-ordered two-point correlation function. Okay, so it's been a little bit of a technical derivation, but I think nothing that you can't handle. Let's now discuss this formula and try to understand what it means, and let me explain to you how we are going to use it.